Good day everyone, I am Erjas and today I'm going to be presenting on a fascinating and rapidly evolving topic at the intersection of biology and information technology, the DNA digital data storage. In a world where data is being generated faster than ever before, from social media and streaming platforms to scientific research and global communications, we are constantly looking for better, more efficient ways to store information. DNA, the molecule that encodes the blueprint of life, might just be the solution. So, what is DNA digital data storage? DNA digital data storage is a method of encoding digital information such as text, images, videos, or software into the chemical structure of DNA molecules. To put it simply, instead of using traditional electronic storage like hard drives or flash memory, we use strands of DNA. This concept may sound futuristic, but it is grounded in well-established biological principles and supported by modern advances in synthetic biology and computer science. One might ask, why DNA? So there are several compelling reasons. Number one is incredible density. DNA is capable of storing an immense amount of data. 1 gram of DNA can theoretically hold up to 215 petabytes of information. That's equivalent to roughly 215 million gigabytes, more than all the digital data held in hundreds of data centers. Longevity. DNA is incredibly stable. Under proper conditions, DNA can remain intact for thousands of years. We have retrieved DNA from ancient fossils and ice cores, which give us confidence in its potential for long-term data preservation. Universality. DNA is a universal language of life. As long as humans or machines can read biological DNA, the data will remain accessible, even thousands of years in the future. So, let's take a closer look at the chemical foundation of this technology. DNA is composed of 4 nucleotide bases: adenine, thymine, cytosine, and guanine. In digital storage, data is typically represented in binary form as ones and zeros. To store this binary data in DNA, it is first converted into sequences of these 4 bases. For example, 00 might be represented as A and 01 as T, 10 as C, 11 as G. These sequences are then chemically synthesized into physical strands of DNA using laboratory techniques. This synthetic DNA carries the same structure as natural DNA but it encodes digital data instead of genetic information. The process of storing digital information in DNA involves several steps. 1. Data conversion. The digital file is first converted into binary code, encoding algorithm. This binary code is translated into a DNA sequence. Special encoding algorithms are used to minimize repetition and prevent errors in sequencing. Third, synthesis. The resulting DNA sequence is chemically synthesized in a lab, creating physical DNA molecules that carry the digital information. This entire process allows us to write digital data into a biological format. And to retrieve the data stored in DNA, the synthetic DNA is sent through a sequencer, a machine commonly used in genetics to read the order of bases. The base of sequence ATCG is then decoded back into binary using the original encoding scheme. Finally, the binary data is reconstructed into the original digital file. This process is non-destructive, meaning the DNA remains intact and can be read multiple times. Several prominent institutions have already conducted successful demonstrations of DNA data storage. In 2012, researchers at Harvard encoded a 53,000 word book, 11 images, and a JavaScript program into DNA. Microsoft, in collaboration with the University of Washington, managed to store and retrieve over 200 megabytes of data using DNA. The European Bioinformatics Institute successfully stored Shakespeare's sonnets, a PDF of the Universal Declaration of Human Rights, and even a short video clip. These projects demonstrate the feasibility and future potential of DNA as a medium for digital storage. Despite its promise, there are still several challenges to overcome. Number one is cost. DNA synthesis and sequencing remain expensive, although prices are gradually decreasing with technological advancements. Speed. Writing and reading data to and from DNA is significantly slower than with conventional electronic storage. And error rate. Errors can occur during synthesis or sequencing. However, error correction techniques such as redundancy and parity checks are being implemented to improve reliability. These are current barriers preventing large-scale adoption, but ongoing research is addressing each of them. The potential applications of DNA data storage are truly exciting. Because long-term archival. DNA is ideal for archiving important historical, legal, or scientific data over centuries. Space missions. DNA's lightweight and durability make it an excellent candidate for data storage in space exploration. Medical and environmental data. Personalized health records or climate data could be encoded into DNA for secure, long-term storage. As the technology continues to mature, it's conceivable that future devices, even smartphones, could include DNA-based storage components. So in conclusion, DNA digital data storage offers a promising alternative to traditional electronic media. By leveraging the natural information carrying capacity of DNA, we can potentially overcome the limitations of modern storage technologies such as limited space, energy, inefficiency, and obsolescence. Though there are hurdles to address, DNA's density, durability, and universality make it a strong candidate for the future of data archiving. That's all. Thank you.